All right, friends, we took a look at curve sketching. This gives us more examples of curve sketching so that we can practice the skills and get ourselves the repetition that we need so that we can be successful. Here's example 2. Sketch the graph of y equals 3x to the 4th plus 12x cubed plus 1. 3x to the 4th plus 12x cubed plus 1. Some things to consider. Do we know the domain? Sure we do. This is a polynomial. Its domain is everybody. Do we know what the intercepts are? Well, we know what the y-intercept is because we can substitute 0 for x. The x-intercepts are harder. Trying to solve 3x to the 4th plus 12x cubed plus 1 equals 0, I'm not sure how to do that. I'm not sure you are either. So I'm not too worried about the x-intercepts at this point. If this were a fraction, we'd be thinking about asymptotes. We'd look for places where the denominator is 0. We'd look for the limits at infinity, but this is not that. This is going to go to infinity on both ends. And so we consider where the function is increasing or decreasing. How do we find that? Well, we take a look at y prime. Y prime is 12x squared plus, nope, that's false. That's terribly false. 12x cubed plus 36x squared. 12x cubed plus 36x squared. Well, that's, I can factor that, right? I can factor that. So if we're doing a y prime chart, there's only 2 numbers to keep track of, the -3 and the 0. Take a moment, hit the pause button, come up with the plus-minus chart. You might be surprised this time. It doesn't alternate. It goes negative, positive, positive. We're so used to those sign charts alternating, but this one doesn't. It goes negative, positive, positive, which means the graph of the function decreases, but then increases, and then keeps increasing. So what happens here? This is a place where the tangent line is flat. It comes to a sort of a flat point, but it's increasing before that flat point and increasing after that flat point. Well, let's consider the concave up, concave down question. The concave up, concave down question, we answer with y double prime. We take the derivative of the derivative. That's 36x squared plus 72x. Well, I can factor that. That's 36x times x plus 2, which means on the y double prime chart, there's also 2 things to keep track of, the -2 and the 0. Take a moment, hit the pause button, make sure you know how to make the sign chart for that. Hopefully you found out that it goes positive, negative, positive, which means that the original function is concave up, and then concave down, and then concave up. So let's put a picture together. What does this thing look like? So again, our figure is totally not to scale. At -3, the original function is at -80. And at -2, the function is at -47. And at 0, the function is at 1. So let's keep track of what we're doing here. We're increasing to here. I'm sorry, we're decreasing to here, and then increasing to there, and then still increasing after there. So it's got to come down and then go up and then go up again. Concave up until -2, holding water until -2. Concave down between -2 and 0, spilling water between -2 and 0. And then concave up again after. So it comes down, flattens out there, goes up, and then up again. That's the function. Okay. One more thing to think about. Let's sketch the graph of g of x equals x squared minus 4 over x squared plus 1. Let's sketch that. Things to consider. Is there a domain? Can we find intercepts? Are we worried about limits? Is this increasing and decreasing on intervals? What's the concave up, concave down behavior? All things that you should pause and consider. So the domain, the denominator is never 0, so this domain runs forever. Where are the intercepts? Well, we can figure out the y-intercept by substituting 0 for x. And we can figure out the x-intercepts if we set the numerator equal to 0. There happen to be 2 x-intercepts. And then we can think about limits at infinity. We can think about what happens to this function as the x's get bigger and bigger and bigger. Well, as the x's get bigger and bigger, the -4 and the +1 don't really matter, and x squared over x squared becomes 1. So there is a horizontal asymptote at y equals 1. Same thing happens if x gets large in a negative direction. The -4 and the +1 don't really affect things. X squared over x squared is 1. Well, let's look at increasing, decreasing behavior. Let's take g prime of x. G prime is quotient rule, right? You can sing the song. For the rest you won't be scared, it's all over the bottom square. That's 2x cubed minus 2x cubed drops out. This is plus 2x. This is plus 8x. That's 10x. So we consider all the places where the numerator or denominator could be 0. There's only 1, because the denominator can never be 0. In fact, the denominator is always positive. And so you can do a sign chart. It looks like this. G is decreasing from -infinity to 0 and increasing from 0 to infinity. So then we look at the concave up, concave down piece. That's G double prime. Well, G double prime, that's the bottom times the derivative of the top minus the top times, oh goodness sakes, it's the chain rule. For the rest you won't be scared, it's all over the bottom square. So what is this? Well, it turns out, and it's algebra to get you there, that this is 10 minus 30x squared over x squared plus 1 cubed, which means that G double prime has 2 special places. One of them is the square root of 3 over 3. That's about 0.577. Or negative square root 3 over 3. That's about negative 0.577. So we put together the picture. What does this thing look like? Well, we know that there's a horizontal asymptote at y equals 1, and we know that it's got roots at 2, 0 and negative 2, 0. And we know that at 0, negative 4, that's the min, right? Because we're decreasing until x equals 0 and increasing after, so that's the min. And we know that at 0.577, where we're down about here, and negative 0.577, where we're down about here, those are the inflection points. So we are, so we're negative, positive, negative. We're concave down until there, concave up in the middle. Oh, that's terrible. Concave up in the middle, and then concave down after that. We're concave down, then concave up, then concave down. This part holds water. Those parts spill water. And you get something that looks like that. Calculator will give you that picture. What's important for you to know? It's important for you to know what are the important pieces of the function. How do we determine if a function is increasing or decreasing? How do we determine if a function is concave up or concave down? This for sure we will discuss when we gather, and I am looking forward to seeing you there.